Okay, and over the last couple of weeks, we've been piecing together everything you would need for this. Okay, if you feel like there's something that you don't have, either mathematically or GC wise, just don't hesitate to ask me. Okay, don't hesitate to say, how do I make GC do this, or I don't know the math behind this, right? So it's both, right? There's a lot of mathematics involved here, and then we need to know GC. That's what we've been learning. So I've tried to give you the pieces, and now I'm hoping that you will put those together. And some have already. So I've seen some good work so far. So you can do it. You can do it. All right. View 1 is just the exact rate function, right? The exact rate function, and that can be changed. So right now, that exact rate, that is this function here, but it would work for any function that you put in. And actually, from a design standpoint, it's better that it's that way. Why is it better that it's that way? For your convenience, or for your you writing this, why is it better that it's generic for any exact rate function that you could put in? So that is in your favor. It's not making it harder. It's actually making it better. Why is that? Yeah, Jose.
Well, let's just put in R of x into our writing instead of full function anytime we need it.
Exactly, right? So every time you're utilizing this function, you can use function notation, R of x, which is a lot simpler and more concise and easier than putting this formula in every time, right? So the fact that you can make it generalizable to any rate function is, in fact, to your advantage, right? So because we've got function notation. Succeeding on this project is a lot about having a function mentality, okay? To do it most efficiently, you're using, in fact, lots of functions. Several functions you're actually creating and using to do this most efficiently, okay? So I'll let you think about that. But hopefully this is encouraging you to really take advantage of functions and function notation to make your life a lot easier, okay? So back to our sliders here. So view 1 is just showing the rate function, and it shows it generated by the current value of x being n. And then view 2 shows the approximate rate function being generated along with the exact rate function, and then this is then for any delta x, right? So now right now delta x is at 0.3. Here it is for about 0.2, 0.07, and so then it should show you it'll show you the approximate rate function being generated for whatever value of delta x you choose on the slider. Yeah, Kendall.
Where do you want the cutoff to be for when the red line disappears? Like what value of delta x?
Okay, so all right, so what she's talking about there is somewhere in here, when delta x gets small enough, then this approximate rate function is almost indistinguishable from the regular rate function. So then, let's see if we can figure out. So there's 0.027.
I think I did mine around 0.03.
Yeah, 0.03 or 0.02 looks like about right. So let's see. It's not. So there's 0.05. There's 0.0463. So 0.04 is fine. 0.04, 0.03 is fine. So it's just and this is a point of the idea, is that when that interval gets small enough, your approximate rate function is becoming indistinguishable from the exact rate function. We can't tell the difference, right? We can't tell the difference. So here's 0.005. This is the smallest. And you really can't tell the difference unless you zoom in. If you zoom in, you can see that it's still all the little teeny constant rates, right? All the little teeny constant rates. Okay, so then, just back to some view 3. will then show both the generation of the approximate rate function and the approximate accumulation function based on that approximate rate function. So it's delta x is for 0.2646. So if you were to graph the approximate accumulation function based on the current delta x and approximate rate function, you get that purple one over there on the right. And then view 4 then does everything that this one does and then just adds on the exact accumulation function, which we want to talk about more today. We really haven't talked about that yet. Okay, so now that hopefully you've looked at it, you might have some questions that would be good for discussion now. Anybody have questions on this? Yes, ma'am.
Do you want us to incorporate, because I know in this particular function there's no a, okay, there is an a, but it's a 0.
0.
Do you want us to make it so that we can have an a not starting at 0?
You don't need to do that. I think there's plenty of challenge here. That's a good question. That's a good question. But and that wouldn't be that much harder. But it's let's just leave it at. You can just I'll always have a b 0. That's fine.
So just like disregard it. The a.
Yeah, sure.
You already did
Oh, did you already do it?
Well, I like went back in and added the a in because I was like, well, what if the a isn't 0? We like change the function.
Okay, great. And so and I will take note of that.
Okay.
Yeah, sure. If you want to put the a in, good. Definitely, it helps your cause, right? Helps your cause. So this one will be worth. It's going to be worth like double the previous assignments. This is really important because it's utilizing everything we've done. I know it's a lot more work for you, so you should be compensated accordingly. All right. Other questions about this? Other questions?
We don't need like the writing on top, right?
No, and the way that I've done that, you can only let's see. So how could you do this?
Yeah, because we need to make individual
Either if you're a PC, are you in PC?
Yeah.
Yeah, if you're on PC, you'd have to do individual symbols. If you're on Mac, this is really easy to do. You can just drag and drop text from you can make a text line. And when you get these more complicated functions, use text to help yourself, okay, and me, but especially yourself as you're designing it. So use text line. So I can come in here and just start a text line. So then I can just okay, but then the problem with this is when you zoom in and out, it doesn't really maintain the same proportion to the graph. It kind of keeps.
How do you delete it after you?
So now see, it doesn't really keep the same proportion. So you can just grab it and grab it off the screen. All right, listen, ready? Did you hear it? Too quiet. Anyway, so that's how I did this. For this, I didn't use symbols. I just dragged and dropped text to make it look right. But then it's like when you start messing with the window, it messes this up. It only looks good in this particular window. Okay. Other questions? Last chance. Okay, so last time at the beginning of class, I said it was an amazing, exciting day, and we didn't really quite get to that part of it. We didn't really make it to the exciting part, so we were going to start with that. So this approximate rate function. So before we do that, let's just ask a question here. Why do we animate this and show the function emerging this way? What's the point of that? What's the point of showing the function using the end slider starting from 0 to the current value of x and then animating it? Why do we do that? Any ideas?
also helps like a student who's watching this like visualize it better or conceptualize it better if they see it as it happens rather than just a static object.
Okay, so if I pause this, so this is now a static object. So he's onto it here. He's onto it. It's like how do students view a graph? So when you see that red curve, how do you think students perceive that, or how do you think they make sense of that? Yeah, Jacob.
Sometimes there's one object instead of a collection of individual points.
Okay, so it's not. So it's just like a wire, right? Like it's just like a coat hanger that we bent, okay, and stuck it on the axes instead of.
Collection of points.
And where did those points come from? What's that? Yeah, so there was a time when all those points got generated. So when students see this, when you see this, do you think or have an image like this? Because this is like a much more powerful image of the covariation of two quantities and all the correspondence points that are generated as those quantities vary together. Then that's the most powerful image of a visual graph, of a displayed graph. And so we want our students to have this image of it when we see this, because this is the way we've seen it all our lives, right? And so unfortunately, then the perception or the conception that students have is not one of covariation. Okay, so it's really encouraging to show the animation is really encouraging the idea that a graph it came about at some point in time. It was generated point by point as those quantities varied together. So, but our typical secondary students in the U.S. don't have any clue that's not going on in their head at all, right? And so working with them with that, and one way you can work with them is to show an animation this way. And so that's why we do that. Does that make sense? Okay, so now we worked hard on this approximate accumulation function. And first we did it piecewise, right? Oh, I didn't do that. Let's see. First we made that thing, we did some examples of creating it piecewise. Meaning a rule for every segment, right? A separate rule for every linear piece of that. And then we worked on writing it in one rule. And in both cases, really, what was that all about? So, where am I? Am I frozen again? Oh, there it is. Why isn't this? Failure. There we go. That'd be my USB port. Oh, it was there for a second. Move the cord and now it's gone. Maybe it's the cord. Yeah, it's the cord. I want to write on the screen. I can maybe do it with my fingers. It's gonna be pretty ugly, but oh wait, it's back. It's back. Okay, so this A function, whether we wrote it as one line or as many lines, it essentially boiled down to what was the main idea that was behind this A function, right? We got a complicated, or we were working on the pieces of kind of a complicated rule, right? It had summation in it. It had the floor function in it. It had other functions involved in it. But really, what did it all boil down to? This A of x function. a approximate accumulation function. So the details are important, but it doesn't have. It only is important if we know what the big picture of it is. So where did this thing come from? Let's go on again. Let's try to write with my finger. So what was the deal with this? In a nutshell. Yeah, Jessica.
Accumulation over completed intervals
Okay.
plus the accumulation in the current interval.
All right, good. So that was a accumulation of the completed intervals plus accumulation of the current interval. But really, so we can even step back further than that. It's the accumulation over many intervals, right? And how did we find that accumulation over many intervals? Summation of what? What's that? The rate? Did we sum up rates? Is that what we did to get this accumulation function? We summed up rates?
Rates were part of it.
We didn't sum up rates. The sum of rates, actually the sum of rates doesn't really make sense. Summing rates together, unless it was like two people are mowing their lawn, right? Two are mowing the same lawn, and you're adding the rates together to get the rate at which the lawn's being mowed. That would make sense. But here, adding these rates together wouldn't make sense, right? Adding these different rates together wouldn't make sense. So what is it we're adding together?
The left x.
Adding the left x points? No,
Something with that x.
no. But so now you're into the details, right? Left x is just a detail of this. We're looking at the big picture. How did this accumulation come about? Whether it was the line by line or the one rule. Summing up. Yeah, Ron.
Is it the linear approximation of accumulation?
Okay, and how do we get that?
It was by using the rate for that interval
Okay, so we use the rate over each interval.
times the left.
The left helped us get the rate. The left helped us get the rate, right? So we got the rate in each interval. Yeah. Times the change in x. Got us what? Change in y. So this is going to be ugly, guys. I'm using my finger here. So we're summing up a bunch of m dx's. I'll just call them delta x for sake of argument here.
Wait, so what's the difference between saying you're summing the rates and summing the rates times delta x?
A huge difference. Someone else. What is the difference between saying summing the rates and summing the rates times delta x? There's a huge difference. Okay, Lauren. But then after this, we need some new folks talking. Yeah, go ahead.
Because the rate times delta x gives you the corresponding change in y, whereas
Right.
adding up just the rates is just giving you the sum of rates, which I don't know what you use up with.
Yeah, right. So rate times this is our telling you.
Oh, I see. It's the current rate times the delta x gives you the change in y delta x.
Make sense?
Yeah.
So in a nutshell, this function is about, so we said summing up all the accumulation from the completed intervals plus the accumulation from the current interval, which is really just summing up a bunch of accumulation from intervals, and each of those accumulations we found by m times delta x, which is really just delta y. So we're just, and that's where accumulation comes from. You just add little by little, right? The word accumulation means add up little by little, right? So this a sub x, this long formula that you got, in a nutshell, is just summing up a bunch of m delta x's, which is summing up a bunch of delta y's, one by one. Okay? So then, oh, I wish I had my pen. Really a bummer. Anybody? No, it's not the stylus. It's the something. I think it's this cord. Anybody have a? Oh, just stay. Oh, here it is. Here's the problem. Okay. All right, so then we're going to call A sub W exact accumulation. Okay? A sub W is exact. So R sub W was exact rate, R was approximate rate, A approximate accumulation, and A sub W exact accumulation. Yeah, it's this chord. So how is it that we, just in general, how is it that we get the exact accumulation function from the approximate accumulation function? Somebody knew. Okay. Guys, people have faces in their computers. Is that being part of the discussion? Okay, so, and maybe it is. Maybe you're doing something that's related to the discussion. It was a real question. So the exact accumulation function. How do we get it from the approximate accumulation function? Where does it come from? Another part of your file, your animation. So, Sam, what do you think? How do I move from approximate accumulation, that purple one, to the exact accumulation, the black one? What's the key concept involved there? Okay. How do I get it better? Peter?
Your delta x gets smaller.
Right. So, right. We talked about how with the small delta x, the rate function is indistinguishable from the actual rate function. So watch what I'm going to increase. I'm going to decrease delta x. Watch what happens to the approximate a. See that?
So as you move the slider to the right, it's actually decreasing in size?
What's that?
Is that because it's going from 0.3 to 0.5, like from left to right?
It's because. No, were you thinking this was moving to the left?
No, I was
No.
looking at your slider and noticing as you move to the right, the numbers are getting smaller.
Right. So yeah, I went from 0.3 to 0.005. So this slider's backwards. It gets smaller as you go this way. All right. So with a smaller delta x, what happens to the rate function? Approximate rate function does a better job mimicking the real rate, and so therefore the approximate accumulation function is going to be better. So going to get closer. So then we get to a point where delta x is so small that we can't tell the difference between actual rate and approximate rate, and therefore we can't tell the difference between actual accumulation and approximate accumulation. So the key concept is a really small delta x. So we still think of it as really tiny constant rates and a piecewise function with really teeny segments, right, over there for a. But this long, complicated accumulation function, we can write now in a much more concise way. So instead of Greek sigma for sum, we use for really small delta x, what do we use? German s. You know that's what integral is? German s. Okay? And we're still summing up. What are we summing up? Still delta y's. Still delta y's. And so now m, rather than being a bunch of discrete rates, is indistinguishable from what? From the whole rate function, right? All right. Are we summing up rates? No. What are we summing up? Yep. And then we use dx for these very, very small delta x's. Okay? So look. So you've got your a function, approximate accumulation, and now this is the exact accumulation, I want you to talk at your table. How are those virtually the same? What do you see in the notation here and the notation here to find every aspect of this that's communicating the same thing as this? Okay, go, talk at your tables. How are these the same? Yeah. Thank you.
Like doing custom. I just noticed that like last month. She's always done it. She's always done it.
It's from A to X or is it from A to T?
So don't worry about that right now. Just you're talking about the similar. How are these how are these representing this? Basically the same thing. So looking at the pieces that you're looking at and the symbols, how are they really representing the exact same thing?
RW is red and R is
Right. We use just the R to be the approximate rate. Yep. R is approximate. Just R is approximate. Just A is approximate.
Is the rate of diffusion is the blue. No, RW is the red. R is the blue.
Oh, we talked on this. Okay, so RW is the.
Okay, it is W is the name of the
Oh, just like doing.
yes. What's the rate of the cycle? Yes. Yes.
AW.
So if it was any function, you could put like
AW is the weight.
A of W is the accumulation of the weight.
Yeah. But there is no weight.
Well, your function is called W.
Yeah.
The function that's up there is W of X.
Yeah. Yeah.
Right.
So AW is like there is no yeah.
Yeah. Right.
Then just A of yeah.
Okay. So let's regroup here. So Josh, what was something you talked about at your table? So what's one similarity or one parallel between these two expressions that shows that they're really the same?
I mean, like, when I was talking, I was a little confused still by it, so there's such a space.
Can you come up with one thing that's a parallel or similar or representing the same thing in this expression versus this expression?
No, I was confused still.
Okay. How about Morgan?
Well, so dt is when dx gets infinitely small, or delta x gets infinitely small.
Okay. Right.
Those
So.
are when our delta x gets smaller, infinitely small, then that's dt.
Okay. Good. All right. Something else. Joey.
We talked about how the summation was like the longer version of the integral,
Okay.
because the integral you just simply you have the end point and the starting point, you just subtract them. And so we just have the summation of the longer version.
So you're thinking about the fundamental theorem. I'm not thinking about the fundamental theorem here. I'm talking about what this actually represents. So yes, by the fundamental theorem, you can compute this a different way. So that's what you're referring to. But this in itself is representing this, and that's what we're getting at. So, Shanley. Okay. Yeah, no, I'm not. So I'm not talking about using the fundamental theorem to solve this. I'm talking about this expression. We want to understand this expression. Genevieve, what do you think?
Well, they're both still a rate times the change in some input,
Right.
but it's
Right. What do we have? Rate times change in independent. Rate times change in independent. And what is that? What foundational principle is that? What is it? How do we see constant rate of change in both of these? Or how do we see it in integral? How do we see constant rate of change in the integral? Right there. dy equals mdx. mdx. Right? That was where this all started a month and a half ago. dy equals mdx. And when you look at that integral expression, it's the foundational principle in this integral expression, m dx, which came from what? Setting our rates to be constant rates and taking each constant rate times a change in x to get delta y by using this constant rate of change principle. Okay? So, yes, I think we hit it all. So, in both cases, we're summing up changes, right? We're summing up changes, and we found those changes by constant rate of change. So this Greek is German S for sum, Greek sigma for sum of changes found by the principle of constant rate of change. Why is constant rate of change so important? Why is it hammered over and over again in all these classes? And in particular in calculus? What?
A lot of things are built off of it. It's like a founding concept.
Okay, and so in particular in calculus, constant rate of change is about? Integral, right? Integration is essentially, at its core, constant rate of change. Many, many times added together. Did you learn that in your high school calculus class? Do you think it's important? Yeah. Okay. Yeah, please.
So I always learned integral as the area under the curve.
Right.
So
I'm sorry.
So I guess, well, maybe I should ask this question.
No, ask. No, this is a good discussion. Yeah.
Well, I'm trying to find a connection between the area under the curve and maybe
Okay, cool, good.
I see it, but I don't.
So where do you see it? So where do you see the area?
Well, so for the integral, we're accumulating. So each individual infinitely many points of where. But see, then I don't know. I guess I need to because I can see it, but I don't know what each thing represents.
So where in this process? So we had this process of we know how fast something is changing. We want to know how much we have. And so given the rate of change, we want the accumulation function. Where in this process could we get sidetracked and head off in the direction of area? Somebody know? Do you see in this process where we could have headed off in the direction of area instead of sticking to accumulation of weight? Can you see it? Oscar?
So like, the way I've made the connection from how it's taught into this was, so as you go further down the x-axis, you get more area, which is you sum it up at the end.
Okay, I've got 4 functions displayed up there, so can you be more specific?
So the R of W.
R of W.
Right. So
Okay.
as you move down the x-axis, your integration is getting bigger. So like the area would be because as you move down, you take that new portion and you sum it up with the rest, which that's how I think that they come out with the area under the curve.
Okay, so he's saying it relates to the rate function as opposed to the accumulation function. Would you agree with that? Angela agrees?
I think that's how it's like how they teach it.
Okay, so we're looking over here and we're thinking, so where does anything else do you see about how area? So he's talking about the area under the red curve would be like this integral. Anything else you see related to area here in this graph over here? Yeah, Kendall.
What about the R?
Okay.
The blue.
Mm-hmm.
Those are like Riemann sums.
Right.
Right Riemann sums. So if you were to draw like vertical lines at the end of, yeah, there you go. So that, oh, is that what, no, that's, oh, that's left hand one, yeah, that is left hand.
Okay. And what is the area of each of these rectangles?
Oh.
Please, go. Say. Who's
If they're a rectangle, you have dx times. Well, that doesn't make sense.
It does.
Yeah.
Delta x times the rate, which is the height.
Yeah, okay. I know. I was thinking dy, but it's not. It's dy.
So, right. So these rectangles that you could form out of that approximate rate function, the area is what? Rate times delta x. Okay. And so, so here's my question. What does area have to do with weight of sand? What does area have to do with weight of sand? Nothing, right? Nothing. Except it just coincidentally, and this is only coincidental that this works out this way because of the way that we graph things in rectangular coordinates. We put y up and then x perpendicular to y, and so therefore it just happens like it's like an artifact, right? It's like this thing that just happens to work out because of the way we graph. That if the constant rate of change, or I'm sorry, the little accumulation is also incidentally multiplying height times base times height to get the area of this rectangle. So, calculus got hijacked in the US. It got hijacked by area. Calculus is about rate of change and accumulation. And in some time in the last 100 years, 50 years, it just integral turned into area of rectangles, getting skinnier to give you area under the curve. And rate of change, and because it's probably easier. But so I don't know, that's a great question. Why? How did that happen? And why did that happen? Okay?
This makes more sense.
I'm so glad you think so. I hope everyone's on board. So she said,
Don't think of it like that.
so Melanie said it's so stupid, it makes so much more sense the other way. And so I hope you all have that same sentiment, okay? Again, what you're looking at here is an expression that means sum up a bunch of little amounts of accumulation, each one computed by constant rate of change. Rate times change in independent. Okay? That's what you, from here on, can think of when you look at an integral. That it's the accumulation, the sum of little bits of accumulation, each one calculated by constant rate of change. Rate times change in independent variable.
Wait, sorry, that's actually.
Yeah, please.
But our rate of change in an integral is going to be the function, because the function.
So if you just generically come to an integral, and it's integral of g of x dx. In the perspective of rate of change and accumulation, g of x is a rate of change function. Yeah, g of x is a rate of change function. Now, I'm not trying to diminish the use of integrals for geometry, right? So we can take integrals now, and we can apply them and find areas, volumes, and all these things, and that's useful and helpful. Okay, but it's not a deep principle the way accumulation and rate of change is. Okay, so if we wanted to find the area under this red curve, well, no, the red curve doesn't have to be rate of change anymore. Does that make sense? But you still use an integral to find it. The integral of that function, whatever it is, the red one, will give you the area under that curve, but then that red function doesn't have to necessarily be rate. But if in the perspective, the context of accumulation and rate of change, your function in an integral is a rate of change function. And gx times dx. So notice, dx is part of the math. This is multiplication. It's not just a little add-on that's telling you to integrate with respect to x. It's part of the math. It's multiplication. It's gx times dx to get dy, right? So I think that's a common misconception too, is that this is just a little thing we tack on to tell us what variable we're integrating with respect to. No, it's part of the math. We're multiplying those two together to get a change in y. There was a question, a hand over here. Yeah, Jacob.
So when we're graphing in our project, the graph on the right, the integral is a representation of what it would be if delta x approached 0. But what we're
Or just maybe a better way to think of this is it's small enough so you can't tell the difference between actual and approximate.
But what we're actually doing is that the summation and like the piecewise.
Are you talking about in your?
We won't be using an integral.
No. Yes. Yes, you may.
We may. Okay.
Absolutely. And so it sounded like I made a mistake in lecture, but I did not. Okay. So Control Shift I gives you the integral notation. So now maybe we should talk about why is it from a to x with RWT dt. Let's talk about that next. But anyway, Control Shift I gives you the integral expression, and you may use that. You may use that. Okay? But notice that you wouldn't need to, because why wouldn't you need to? So suppose I didn't tell you that, and we still wanted to graph this representation of the exact accumulation. You really need integral. Why not? Use your one-line a function, and with delta x being really, really small, and it will get a graph that's indistinguishable from the integral graph. Okay, so that's the whole point. That our one-line accumulation function is essentially the same as this notation for very, very, very small delta x. So small that you can't tell the difference.
Is that 0.005 small?
Let's take a look.
What is the purple one? That looks good.
Yeah. So 0.005, in this view of it, they land right on top of each other. If you wanted to be sure, you could do 0.001 or something. So yeah, so actually using the integral expression in your file is optional. You could get that exact accumulation by using a small enough delta x with the a function that we built. Okay, so why the x and the t? This is important. So why the x and the t? Let's go back here and make it not so messy. Why can't we just do this? So I'll just call it a sub w star. So why can't we just do a to x rw x dx? Why do we need this to introduce this new variable t in there? So the way you can think about this, I'll give you a second, is evaluate both these functions, or what would they evaluate, say at, let's do it at 1, okay? So think of what would AW of 1 be, and what would AW star of 1 be, based on the way that we've set the rule up. So just take a moment to investigate that with the people at your table. So why is AW of 1 get us what we want, but AW star of 1 does not? Does not get us what we want. Go, work on it. So write out what both of them equal, okay? Use the rule.
Doesn't they all have to be two?
write out what both those, the function notation express. Write out what both those function notations express. AW of 1, AW star of 1. Write out both of those.
Like if I define a of x equals t squared, whether I say a plus, it's gonna give me the 1 because I told it to
Yeah, so you gotta, there's a couple things, not only the x. I don't know how GC knows to graph what you intend to graph, but this is not right for a couple reasons. So, yeah, the x for one thing, and then there's something else that's not quite right. So, yeah, so think about that. But for some reason, somehow GC knows what you're intending and is doing that correctly. But yeah, so think about it. But if you keep talking to me about it. Let's do it another time. Did you already do this?
Yeah. Yes.
Dots.
Yeah, just carve out for specific dollar. Go away.
Let's see what you're talking about.
How the line moves down and there's little dots right here.
Oh.
And then it goes away.
I'll have to look at your files and do that. I've never seen that before. Okay, somebody new. Who discovered something? Daphne, at your table, did you come up with anything? Okay. Right. You nailed it too. So when you do a star of 1, yeah, she's got it right on. When you do a star of 1, you get the integral from a to 1. That's fine because we're starting at a. We want to get all the accumulation up to 1. That's fine. But how are we getting that accumulation? R sub w of 1 dx. So how is it going to accumulate from a to 1? How is it going to accumulate from a to 1? Is it going to accumulate according to little constant rates all through here up to 1? Yeah, it's just going to, what is it going to do? So it's going to take the rate at 1, and you're going to accumulate from a to 1 at that rate the whole time. So this is the rate. If you use the x there, and for a particular value of x, you're going to get a constant rate for the whole interval from a to your final value of x.
How does it know what t is?
What's that?
How does it know what t is?
So what t represents then, t represents all x values from a to x. So now you're talking about this one, right?
Yeah.
So now this is our independent variable for r, and so t is going to increase from a to x along the actual rate function. So here we get the actual varying rate function from a to x rather than the constant rate at the end for the whole interval. Does it make sense?
It's just like a dummy variable, right?
Yeah.
Put anything in there, it doesn't have to be.
Right, it's a dummy variable, and so because it's not specified, then it takes on all values, right? It's going to take on all values of the independent variable starting at a, ending at x. If you go from a to x, rwx, then for any given value of that x, you're going to get a constant rate for your whole. You see it? Because the second version is going to do this. That's a constant rate. That's just a number. R sub W1 is a single number. It's not the rate function. It's the rate at 1. And so you're going to be accumulating at that constant rate for the whole interval, a to 1.
I think we just proved it doesn't matter which variable you
Yeah, I
use.
used an emoji.
Yeah, sure. Yeah, and that's like anything, right? T, there's nothing special about T. So U, V, whatever you want.
I think we were confused because last time we used T, it was the parameter
Oh,
that
okay.
from 0 to 1.
It's not about T being a parameter.
Okay.
It's about any other symbol besides X.
Okay.
Just like it's a dummy variable like a function. So it's a dummy variable like a function. So U, right, emoji, whatever.
Isn't T reserved though in GC for that parameter that defaults from 0 to 1?
Not so dummy. You can do anything for dummy variables. Like we can define functions using X, right? X is reserved for graphing things like the X-axis. But if you use it, you can use it as a dummy variable, and doesn't mean the X-axis.
Okay.
That's like when we define. We do this all the time, right? So here, X is different than. So in those in those lines, X is treated differently. Remember this? We didn't talk about this. Here, X is just a dummy variable for the independent of F. Here, X is about the X-axis and displaying a graph on the X-axis. Okay. So same issue. T, when you as a dummy variable, can be used for a dummy variable for a function. Okay, so this last discussion about why we need the T, a new dummy variable T or U or V instead of our X dx. Any questions about that? Okay, so you got this really important project, and so hopefully this is as much or more about the mathematics of creating integral, this project, other than trying to figure out what to type into GC, right? So what to type into GC is about you really understanding the mathematics of building up the integral expression, which is foundationally about constant rate of change, okay? Last chance for questions. So we're going to continue the journey, which is to talk about the importance of average rate of change. We still haven't really talked about why average rate of change is such an important topic, also emphasized in our program. But let's take a break. Let's do something else for a while. Okay? Is that okay? We'll come back to that because I think it's just good to change it up. So we conclude here with this discussion of, or we pause here with this discussion of what's so important and why is so much emphasis on constant rate of change. And we answered that question today. And then you've got your project to practice and really understand the mathematics behind it all. So, shifting gears. Last chance for questions on that. Okay, so if we want to talk about something new, here's a little intro to something new. Here's a question. Let's take the answers off the table here. Let's just make it open-ended. Okay. Caterpillar walks on the wall from point A to point B along the path shown. Is the caterpillar's height above the ground a function of time elapsed since the caterpillar started moving from point A? I want you to discuss this question at your tables. So here's caterpillar walks from A to B along the path shown. Is the caterpillar's height above the ground a function of time elapsed since the caterpillar started moving from point A? Go. Talk to your tables.
It'll still be.
It's just the graph doesn't
Well, that's not the actual.
Yeah, that's the graph. So that's just like the graph of function. Yeah, so that is the heights from time. And he was just at the same. That's just but it's not a function of time. It would show that he went back.
So this is actually
That's just it. It's just showing the height relative to the grade. So it's literally showing, it doesn't say that's all I'm saying, like,
We don't have time.
so you can actually guess an height.
Okay. Do we have enough time to discuss? So, Camry, what did you guys talk about? What do you think? Yes or no? Is height above the ground a function of time elapsed since the caterpillar started moving?
We said yes.
Why yes?
Because as time progresses, like it's either moving up or down.
Okay.
So this graph isn't, it's not like an actual representation of like the time graph.
Okay, so what you're looking at in the illustration is not a representation of the function being asked about. Okay, so why is the function being asked about? Why is it a function? Brianna, why is it a function?
because for every time value, there's going to be a different height above.
So for every time value, there's going to be
One. Yeah, a single height for that single.
a single height for any point in time. Otherwise, then the caterpillar could be in two places at once. Impossible, right? So at any given time, there can only be one height. So did you all conclude yes? The function? Okay, cool. So now this curve, is this, so here's where we're going. Is this curve a function? Is this curve a display of a function? Now let's go back to the illustration. This curve, this path from A to B, is it a depiction of a function? Ryan, what do you think?
I want to say no.
Okay.
Just because based on what your x and y values are.
Okay. What? So
Or your
yeah. What are the x and y values in that picture?
your horizontal distance.
Okay.
And your vertical distance.
Okay. So is height above the ground a function of horizontal distance from whatever this reference point is? Are we all in agreement that that's no, right? Yeah, because for different horizontal distances, you could have more than one height. Okay, but I ask again, is this curve a depiction of a function?
It's a depiction.
Yes.
Of a function, of a function, a real function.
Yeah. Right. Yeah.
So, Jacob.
It's just the independent. It's a representation. It just doesn't have the independent value.
So, okay, so
It's still the caterpillar height. We're not saying it's the function, we're saying it's the fixed.
So if that's the case, then it wouldn't be a function.
So we said that height is not a function of horizontal distance.
Yes.
Is that curve a representation of some function? Ron?
I would say that it's a representation of a function of the height and ground with respect to time, because it does show it moves but it's not a function of the height around.
But that curve would be a representation of height versus time, right? That curve.
That's what I'm saying. Well, then I'm saying that this is not.
Okay. Yeah.
I say it's not because that like one horizontal distance, he could be at two different heights at two different times, but we're not talking about time.
Right.
But there's two corresponding heights that he could be. We don't know which one.
Okay. So you guys are kind of still latching on to these quantities. So as long as you are holding on to these two quantities, we're all in agreement it's not a function. But could this curve depict a real valid function? And if so, how? Chloe, any ideas? How could it? You don't think it could? See, how is a function defined? It's defined by its independent and dependent quantities, right? Go ahead.
We could have a parameter of t within that, like in our parametric equations.
Time since start moving? Okay. Okay. So what dependent variable would be represented by this curve that would give us a true function?
A specific you'd have two parts of it, wouldn't you? Like you'd have like each point in time would relate to a horizontal distance and a vertical.
And those two things taken together would give you what?
Your dependent variable. Your position.
Position. Location. Isn't this a function? And isn't the curve a representation of those two quantities? Time since starting to move and location. So what do you need then to express location? Jacob nailed it. What do you need? Right, you would need your x coordinate, what, as a function of time? And y as some other function of time. But these two things taken together as a location, an x and a y, would be a function relationship, a function of time since starting to move, right? Because given any time since starting to move, can the caterpillar be in more than one location at once? No, so pick a point here. Let's call it T1. There's a corresponding, what, x1, y1, which would be the dependent variable. Now it's the ordered pair, right? So their variable is ordered pair. Does it make sense? So that's how you can think of that, exactly that curve still being a function. If your independent variable is time and the dependent quote-unquote variable is location, which we would have a ordered pair. Yeah?
I see what you're saying, but this graph doesn't give us anything about time. So how can we just decide that time is, you know what I mean? Like, it tells us nothing about time. It could have stopped at one point and then kept going. We don't know.
Okay, so this is the idea of what we call a parametric function, which we still graph in the xy plane, and we don't, so t is called the parameter. It doesn't get displayed. It doesn't get displayed.
Like, I understand a parametric function, but we still don't know, like, he could go faster. You see what I'm saying? Like, because I do understand what you're saying.
So
Right, but my point is that this graph is about how long.
So okay, right. So it doesn't show rate.
Yeah.
I agree, but is that curve a representation of the function nonetheless?
Sure.
So that's all I'm getting at. So that was my question was, what function could this curve be a representation of, even though it's not showing rate, okay? Okay, so in GC, is it a function? Is it a function? Melanie nailed it. It could be, maybe. Is y a function of x? No. Y is not a function of x. So saying is it a function, you can't answer that question unless you know what your dependent, independent variables are, right? A function is defined by what two quantities are in a relationship together. If it's the relationship of x and y, that's not a function, right? But if it's the relationship of x and y to some parameter t, then it is. And so this is actually 2 sine of 8 pi t is x. And y is cosine 6 pi t. So in GC, to set this up, to start a parametric function, which is going to be our next little jaunt here, control 2. Control 2 gives you this vertical like vector, x, y, and then you can do equals and do it again. And then you can replace x and y with what you want it to be. So x squared minus 3 and no, sorry, t. So now here we want to use the t as the parameter, built-in parameter in GC. Sine t to the cosine t. I have no idea what this will do, but this should be cool.
How does GC know when to take the sine and cosine of it if we don't use parentheses? Is it just everything after sine or cosine?
Well, that was kind of boring. But so notice, so why is this boring? Because if you notice over here, real fine print, it's going to graph all the ordered pairs x and y for this range of t, which I only have from 0 to 0.5. So we need to show more to see what's going on here. So let's go 0 to 10. That's 0.1. I got high hopes here. Something like a Nike swoosh, right? Oh, wait. Ooh, it gets better. Let's see. Oh, you see? We need more here. You all doubted me. All right. Okay. So the next we'll do a little unit here, and we're going to talk about parametric functions and use GC to do parametric functions. So Tuesday, we're on track to be finished Tuesday with the big project. It's a major project. It's worth more than